Hello wonderful people, welcome to Cosmology Talks. This is a talk about quite an ambitious project, scrutinizing methods that go beyond the simple power spectrum or two-point function in cosmology. The power spectrum is really the lead character so far in the story of statistics in cosmology. It's ever reliable, it's trustworthy, but it's not necessarily sensitive to all new physics, and it definitely doesn't contain all the information available on nonlinear scales. So we do have to go beyond two-point statistics. But exactly the issue that makes going beyond the two-point function useful makes any statistic beyond the two-point function difficult to model and validate. One is more or less necessarily dealing with the messy, nonlinear scales where baryons and astrophysics show up. This makes it all the more important to scrutinize these methods and make sure we trust them. This was the goal of the people here today. They analyzed, using novel beyond two-point statistics, they analyzed mock data that someone else produced. So crucially, the analyzers didn't know the correct answer, but someone else does. Such masked data analysis challenges have been done in the past and are a very valuable validation tool for methods in cosmology and in all science. But for these particular methods, the stakes are perhaps higher and the research is more vulnerable because the very novelty of the methods means the community is more skeptical and therefore the consequences of failure might be higher. This talk and the discussion around it is very interesting, and I would like to think a valuable resource for anyone interested in running their own mock data challenge, or anyone who wants to get an overview of the types of data analysis methods available in cosmology beyond the power spectrum, because each method receives a short summary. There are also interesting thoughts and discussion shared on where the additional information is in the data and how best to extract it, including some digression into what it even means to be best able to extract the additional information. In other words, what do we actually want as cosmologists doing cosmology? I won't introduce everyone now, as there are in total 9 different people in the video and 7 different methods introduced, not to mention 25 people involved in the challenge in total. So instead, the speakers will introduce themselves as they speak first. So, welcome everyone. Would one of you like to start by telling us briefly about the challenge and what it is all about?
So, hello, I'm Elisabeth Krause, and I'm the first today of the Beyond Two-Point Collaboration, telling you about our parameter mask data challenge, or as the participants like to call it, our friendly discussion. We are all interested in how to best extract information from the galaxy distribution, and many of us have been developing different statistics to better capture information in the galaxy distribution than old-fashioned methods do. So here we come together to try these methods on mock catalogues, for which initially only some of us organizers knew the cosmology parameters. For example, Yosuke, Kobayashi and Andrés Salcedo did not even tell me, so that my face would not tell participants in discussion how things are going. And then everyone went, did their homework, tried to verify that their method worked, and reported cosmology constraints to the organizers. And then we compare, and then we really start to learn what works and where future research might be needed.
Yeah, this is very exciting. I think later on we'll get into the kind of psychology of how this process felt to you guys as participants of it. But for now, let's just stick a little bit to science. So if there were only 2 things that people remember from the paper or this video 6 months from now, what would you want them to be?
Scratch that qualify novel statistics for statistics beyond the power spectrum. These methods are really ready or getting ready for data analysis, and that parameter mask challenges can be a really useful tool to understand methods better. And if I may add one third point, we welcome new submissions anytime.
Would you then be redoing the whole process? Because I guess now that the data is unmasked, new submissions have a kind of like a cheat.
That's why we only report fractional parameter offsets. So one should not easily be able to reconstruct the cosmology parameters from the paper. And we organizers commit to unmasking submissions at later times, and also then to update the summary plots on the GitHub repository describing the challenge. Of course, then later submissions can use those plots in their own papers. We are probably not going to regularly write another big paper like this. So if I may just tell you a bit more why the parameter masking is so useful. A key aspect here is that, of course, the statistics matter a lot, but so does the modeling. And in particular, how far into nonlinear regime can a particular statistic be modeled? Naively, one could say that number of modes scales with k max to the third power in Fourier space. So the further one can reliably go nonlinear, the better. And that's really where the parameter masking comes in, because that means that each analysis team now has to sit down and figure out how to test for internal consistency of their method and figure out how far they can push their modeling without just relying on knowing the parameters of the simulation.
Yeah, what was the history of this idea? Where did it come from?
So, of course, we are not the first to do a mask challenge. That's a quite common tool in cosmology and probably in other fields as well. Most recently, there has been the PT challenge that really established the reliability of EFT-based methods for galaxy power spectrum analyses. So when we were thinking about putting together a workshop at the Aspen Center for Physics in 2022, we thought, okay, let's put our cards on the table and see how this works for novel statistics.
What I wanted to kind of dwell on a little bit before we get to the main presentation is, I guess, just the philosophy of why you've done this. Because I guess a lot of the time behind closed doors, groups do this anyway. You make mock data, you check whether you can reproduce it, but you know the parameters there. And then there's the other side of things when the actual observation gets made. Obviously, you then calibrate all of your systematic issues that you might be worried about and make sure that you get the data right. But there you don't know the final data. On both sides of the thing, you're kind of safe, right? Because if you are doing something behind closed doors, you're completely safe. You can do whatever you want. And then when it's the actual observational data, because we don't know what it is, if you get a whopping 5 sigma tension, you guys might be the people who've discovered something new. So this type of analysis that you've done now seems like the kind of uniquely brave and terrifying thing, because you've got nowhere to hide anymore. And I guess that's why it's so important.
I mean, you said exactly the point on why we did this, right? Because we want to avoid being biased by our own knowledge of what we're trying to fit. So by doing this kind of tests, you're going like out of your confidence zone, right? You might be even trying to fit some set of data that you didn't even think about, right? So, and that's very helpful. But not only that, in my case, at least in my personal experience, I learned a lot from other methodologies. And some of them, I wasn't even aware of them. So it was very helpful in that sense.
I think it's especially interesting to do this kind of challenge for the statistics that are just being developed, and statistics that we consider like novel from this point of view. And it's also especially scary to do it with those kind of statistics, because you are in a situation where you need to like show the community that this new thing that's been developed actually works and can be applied to real data. Like, for example, if something like the power spectrum or the correlation function, which has been established for many years for now, if you show that it doesn't work under certain circumstances, that's still very interesting, and then people would be very interested in seeing why a method that is supposed to be very robust doesn't work under certain circumstances, right? If on the other hand you are proposing a new method and the community still doesn't have any reason to believe that method should work with real data, I think there is like an extra challenge in trying to overcome this fear of not perhaps completely ruin the reputation of a new statistic that's been developed, right? But I think that shouldn't prohibit us from doing this kind of challenge, because as Marco just said, the whole idea is to just learn from this, right? And whatever the outcome is from the challenge, whether you get biased constraints in the end or not, you will always learn something about the process, right? And if you get biased constraints, you learn something about why the model is failing, what's causing the model not to be robust under certain circumstances. So in the end, I think the right attitude is just to ensure that we are always like trying to learn and not necessarily trying to compete and win the challenge.
Let's go into details now about exactly what was done. How was the mock catalog? How were they set up? How were they masked? And then what were the actual methods that have been used to analyze the data?
Okay, well, thank you everyone for that introduction. I'm Andrés Salcedo. I'm a postdoc at the University of Arizona. And I, along with Yosuke Kobayashi, a former postdoc here, produced the galaxy catalogs that were used for the challenge. And we're part of the organizing team with Elisabeth. So I'll run you through those. So what we've done is produced 3 sets of galaxy mock catalogs of increasing complexity. What they all share in common is that they are based off of M-body simulations from which halo catalogs have been extracted, and then Yosuke and I have populated those halos with H-OD galaxies. So the first 2 sets are each a set of 10 realizations of a 2 gigaparsec box at redshift 1. The first set of those 10 are populated with real space galaxies. The second set with galaxies in redshift space. Those simulations were run with the Ginkaku code by Yosuke. And then we have a final simulation, which is the most sort of realistic and complex, which is a light cone galaxy mock in redshift space The underlying simulation there is Abacus Summit Lycone. So Abacus Summit is a suite of cosmological n-body simulations. It covers a broad range of cosmologies. There's a ton of volume, and they all have very nice mass resolution. Those are publicly available. They're an excellent resource. So what we've done then is we've selected one of the ΛCDM Abacus Summit Lycones and populated them with galaxies in redshift space. We've selected them so that they live within this redshift range between 0.8 and 1.3. And then we sort of just trim and clean up the footprint to make it simple and easy to provide for the participants. Initially, the parameters and also the form of the parameterization were known only to Yosuke and myself. Later on, they were revealed to Elisabeth, but they remained masked to all participants. And then the final piece of information that we provided was the ΛCDM prior that all three of the cosmologies were drawn from. We've provided these catalogs publicly. What that means is that there are basically three sets of catalogs, which are tables with galaxy positions. There's a mask associated with the Lycone, and then we provided additional information that the galaxy halo connection model is HOD based. The catalogs are free of systematics, and that the cosmologies are drawn from a ΛCDM prior, which we've made available. And at that point, the organizers are fairly hands-off. So the teams have the catalogs, they decide what they want to do with them, which means they define their data vector, measure it, and then they do validation and covariance calculation. And once they're satisfied with their analysis, then they submit the results to the organizer team, and then we process them. So here I just want to emphasize that all parameter values will remain masked to enable future analyses. And so Elisabeth, Yosuke, and I are committed to processing any submissions from other teams. And if you're interested in doing one of those submissions, then you should look at the GitHub link that is posted on the slide. You can find the catalogs there, and you should feel free to email Elisabeth, Yosuke, and I with any questions or with a submission.
What type of survey were you trying to mimic with these mocks?
Right. So in this case, this would be more or less mimicking a spectroscopic galaxy redshift survey.
Like a BOSS one, a DESI one, a very future one?
I would say akin to DESI. Some of the details there would come down to systematics. Right. So then once everyone has satisfied themselves with their analysis and their validation and has submitted their results to the organizer team, we basically process them for unmasking. So what this means in this context is we produce this plot, which is being shown here. This is showing marginalized constraints in omega m and sigma 8 in the left and right hand panels in terms of fractional offsets from the input truth cosmology, which is indicated with the dashed vertical line. And so Elisabeth, Yosuke, and I process these. We set a time for the telecon unmasking. You can see in the figure that we've anonymized each one of the submissions. So each one of the teams was informed of what its color identity was, but was unaware of the other team's identity. And so we basically all got together and with some trepidation, I suppose, revealed the figure. Fortunately, everyone, I think, was satisfied and happy with the results. As you can see, all the analysis teams are more or less recovering the input cosmology. At this stage, there was the opportunity to gracefully withdraw, but since everyone was satisfied, no one actually took that option. And at that point, then, it's time to do post-unmasking analyses, any tests that are motivated by the results. So at this point, I'll hand over to Min to talk about the high-level unmasked results.
So thank you, Andrés. I'm Min, postdoc at University of Michigan, moving to Kepler IPMU in the fall. And today I'm very excited to present the results of this challenge. So here is the plot that Andrés showed. But now with the results are all labeled with the team names and the scale cuts of each analysis, either in terms of minimum separation or the maximum Fourier mode involved in the analysis, depending on whether the analysis is performed in spatial basis or Fourier basis. So from top to bottom, we have density split clustering, two flavors of K's nearest neighbor, K and N, power spectrum loss by spectrum, models with the effective field theory, EFT, P plus B, power spectrum models with the Barco emulator, Barco P, and finally, power spectrum loss by spectrum models with simulations, SBI P plus B. And I believe Misha will introduce the teams further, and also Misha and Enrique will explain the details of EFT and also HOD modeling in a bit. So for now, let me just focus on the result. The key highlight is that the ground truth is within 95% confidence limit for all the 1D constraints on either omega m or sigma 8. And another takeaway I would also mention is that all the constraints are very competitive given the volume and the density of these galaxies. These are results from the redshift space mocks. So you have information from both the clustering and the redshift space distortion. By mean of 10 realizations, what we mean is that each team average their data vectors over 10 realizations, and this is to suppress cosmic variance. And this cosmic variance suppression means that the possibility or probability that any posterior picks more than 1 sigma away from the ground truth is actually 0.16%. And by analyzed in flat lambda CDM, we mean that all analysis vary and marginalize over on the flat lambda CDM cosmology parameters in the reported constraints here. Finally, there's one more detail. Basically, you see here the constraints are reported in 2 categories: the fixing and freeing the south horizons scale at decoupling. And the reason is because the 3 analyses on the top rely on Abacus summit simulations, which I believe fixed theta star, and the SBI P plus B analysis rely on Quixote simulations, which freeze theta star. So to facilitate the constraints, the EFT P plus B and Baco P, the analysis was submitted with fixing and freeing theta star, and you should really compare the constraints, or you should look at them in 2 categories.
Can I just try and make sure I understood a few things? This caveat in particular. So would it be true that if this analysis was just done on 1 realization, that there's like a 30-something% chance of a 1 sigma, the normal Gaussian definition of 1 sigma, that there's a 30-something% probability that you would be 1 sigma away? Then because it's been done on 10 realizations, you kind of divide by the square root of 10.
Exactly, yeah. So that's how you get to the 0.16%. So now basically you're looking at a little bit more than 3 sigma actually. So 1 sigma here is equivalent to a little bit more than 3 sigma. One thing I should mention or clarify is that this is basically only the case for 1D without accounting for any parameter degeneracies.
Okay. And so then if I want to say, look at one of these methods and say, how good do I think it is? Do I have to now multiply by square root of 10 to see how good it is? Or
no, you don't have to do that for the constraints. So that's a very good point. So on the analysis, assume a covariance correspond to 1 single realization. Cool. Yeah. So moving on, now we look at the same result again, but now in the projected into the 2D plan of sigma 8 and omega m. And now you can see that the ground truth is well within 68% confidence limit for all the results. So again, this is, at least to me, very promising given the large dynamic range of scales that all of these statistics and analysis are probing, and all the different kinds of statistics. But the results are all consistent with each other, and more importantly, consistent with the ground truth. So that's the redshift space analysis. There are also the analysis for the light cone mock and the real space snapshots. For the light cone mock, we have the void team that analyzes the data using either void galaxy cross correlation function or the void size function, and again, the EFT P plus B team. It is important to note here that the light cone mock only has 1 single realization, so there's no cosmic variance suppression here. So it's normal, totally normal to have a little bit more than 1 sigma away from the ground truth. Finally, it's the real space snapshot result, including the Baco P, EFT P plus B, and the field level Bayesian inference modeled with EFT, so EFT API. One thing to notice here is that the reported constraints are on sigma 8, assuming fixed on other cosmological parameters to the ground truth. And yeah, again, so we can see that the results are all within 95% confidence limit for all analysis. And given that I'm doing the EFT API analysis, I can already comment that we believe, or we think that we know the reason for this residual bias that we are observing now. And I believe Misha and Marcos will get into that into the post-unmasking study. To summarize, the result is beyond 2-point methods might be novel, but they are at least mature enough to pass this parameter mask challenge. However, there are some caveats, which are result access where the certain analysis is unbiased for these specific mocks in the data challenge. They do not generalize to other extended cosmologies or across parameter space. And one more thing is that the results that we report here do not establish whether the reported uncertainties fully reflect the true uncertainties. So because of that, we don't recommend that the reported constraints should be used to compare like one-to-one as a relative measure of the information captured by each of these statistics and methods. So for those, I believe that would require future challenge with more simulations and more mocks that spanning across cosmologies and model parameter space.
Should point 3 be obvious to me?
The mocks in this challenge for each given setup, they're all generated at a specific point in cosmological and HOD model parameter space, right? So these methods were tested at that specific point, but not across the whole space of parameters and degrees of freedom.
So if the real universe had a particularly different value of omega baryon or halos formed in slightly different ways, then because you've only constrained yourselves on the mocks where omega baryon had a particular value, that might not be the same.
What at the simplest level, I mean, you cannot measure the information content in each of these statistics at just one particular point in parameter space, because the actual feature information, for example, can vary between points in parameter space. And another point is that each of these methods or analysis can be tuned and optimized for that particular point, but that doesn't guarantee that they will be robust and they will give the same constraints at another point.
Yeah, I think that maybe two things that we can expand on here. The first one being the question you were asking earlier, right, Sean, of, okay, this 1 sigma deviation could be because of the statistical fluctuation, or it could actually be because the model is biased, right? That's something that we can't really answer with this challenge to some extent, right? So what you want to do ideally, and perhaps we can go back to in the future challenges, is to really run a large number of realizations so that we can assess the error bars in a frequentist manner, right? So run coverage tests to check that 68% of the times you actually get the right value within 1 sigma, right? That would be the ideal. Obviously, that's expensive. So that's why we haven't done it, but future challenges should definitely do that, because you could get tighter constraints, but actually they might not be well calibrated, right? So they might be prone to be overconfident, and that would be something we need to check. And I think the other aspect that maybe we could mention that now is the fact that there is no mock challenge that could be said to answer the question of what is the statistic that optimizes surprises, right? So I think we shouldn't obsess over information content, because no one really cares about the actual uncertainty on omega matter. We only care about it when it tells us something interesting, right? And we can't set out a challenge that does that.
I'm Misha Ivanov from MIT. So I'm going to start off by saying a few words about the participant analysis. Here we're showing some relevant parameters for each method. The first relevant parameter is the gravity solver, or like the way to describe gravitational nonlinearities. And well, basically for all these different categories we introduced, we roughly broke them into analytical and computational. So for gravity model, we have basically 2 things, either n-body simulation or some perturbation theory kind of calculation. Then the second relevant parameter is the tracer model, or the galaxy halo connection between galaxies and underlying dark matter. And again, we have the variety of methods ranging from linear bias all the way to fully numerical HOD modeling. And then we also have the model evaluation. This is the third relevant parameter. And again, either we calculate the theory vector analytically or using different, emulators or galaxy mocks. And then also have the last, column is the covariance. And again, here you see all possible kinds of methods ranging from analytics to, fully numerical to jackknife data-based methods. So here we represent really, the biggest diversity of different approaches to these different aspects. Yeah, one of the important points of this challenge is to verify your model, to verify what you're doing. So as Elisabeth mentioned, naively the information scales like the number of modes, so Kmax cubed. So obviously, the higher Kmax is, the smaller the error bars are. And there's always this trade-off between, potential bias, because also, when you push to very small Kmax, to very small scales, large Kmax, you're most sensitive to nonlinearities. And the nonlinearities are the hardest thing to model here. So there is always this trade-off, and there are different tests that one can do, and each method they have their own set of tests to validate their results. One example of this that we did in the context of EFT is we did the parameter drift test. So basically, we produced many parameter constraints for different choices of kmax, and you see that at some point the contour starts shifting. And here, as Min mentioned, we're using this data vector with suppressed cosmic variance. So for instance, if we see this 1 sigma shift, then this is likely to come from some uncertainties in modeling. So for instance, you see it in this perturbation theory at kmax 0.3, we have this shift, so okay, we cannot trust this. But for kmax choices which are slightly lower, for instance 0.2 or 0.25, they both seem to be all right. And then in this case, we can use some other consistency checks. For instance, in the context of this perturbative techniques, the perturbative nonlinear correction should be smaller than the linear theory result. So on the plot on the right-hand side, you can see that, well, we basically, here I'm plotting delta P, the nonlinear correction versus the linear one. And at kmax point, at k.2, roughly it's 10%. So you can say that, oh, look, perturbation theory sort of makes sense. But as you push to 0.25, you see that it grows very fast. And at 0.25, it's already 50%. So 50%, if the one loop correction 50%, then next to linear order correction is going to be 25%. So it means that the kind of perturbation theory is not under control. So we can reduce kmax 25. So this is an example of the internal consistency check that one can do. So basically, from the technical side, the most important part of this challenge was to come up with as many different ways to validate the model and, as many, provide as many consistency tests as we can and run them and show that these results, they work and make sense.
Sorry, I think you said this, but I didn't fully understand. The on the left-hand side plot, the data here is what? I understand that the difference between the gray line and the red line, but what are they overall?
Yeah, this particular plot is for the power spectrum, but in the paper, basically almost every single team, they had used the same method to validate this parameter drift plot to validate their choice of kmax, because this is the hardest choice that one has to make in this challenge. Okay, in the context of this EFT, basically the idea is, on the left, you can see the snapshot from a galaxy simulation, and on large scales, on very large scales, it seems that the galaxy distribution is basically, looks like a Gaussian random field. On small scales, it's very nonlinear. We see all these filaments. So on very small scales, obviously, things are super nonlinear, but on very large scales, they are linear. The idea of the EFT is to take advantage of this linearity on large scales, because linearity means simplicity. So basically, this story about this interplay between different scales, this story is manifest when you take a look at the galaxy power spectrum on the right, and you see that on large scales, so small k, linear theory is kind of doing a good job. But then as you go to higher k's and smaller scales, so linear theory breaks down, but it breaks down not horribly, it breaks down kind of in a controlled way. So the difference between linear theory and data is smallish. So that's why up to k, let's say 0.2 or 0.3, we can take into account nonlinearities perturbatively. And we can do so because the galaxy distribution features several scales. So we were in the regime of some scale hierarchy. So all the difficult physics that we cannot model analytically from first principles, it's controlled by a scale which, well, like here I call air halo, typical size of the halo, which is roughly a few megaparsec. And you can see it on the plot as the size of the large sort of clump of matter on the inset. And then on scales larger than that, so for scale separations, let's say 100 megaparsec, relevant for the BIO studies, the distribution of galaxies can be modeled using some coarse-grained degrees of freedom, such as the large-scale density field and velocity fields. And in this regime, we can work out an effective fluid description. So this is the idea of the effective field theory, Flaschke structure, and EFT basically builds on the previous perturbative idea. So that date back all the way from Zeldovich, Skochimara, and so on. So this is a very continuation of a very old tradition. And in the challenge, the EFT results that I'm using, they are based on this realization of EFT that I developed times less perturbation theory. On this plot, you can see the output from simulation, galaxies, and also dark matter. So dark matter structure is in gray, galaxies are yellow. So you can see that roughly this sort of trace, the galaxies that trace the underlying dark matter field. And if one uses EFT to describe the galaxy dark matter connection, then one can say that on very large scales, basically the only thing that we can write down, the only kind of correlation we can write down is linear. So the galaxy over density should be linearly proportional to the dark matter density field. And then the dark matter density field itself on small scales becomes nonlinear. So we need to take into account higher order corrections. So we should really interpret the right-hand side of this expression as a Taylor series. And we have a linear term, but then there will be a quadratic term, and also there will be higher order terms. For instance, at some point, you also can write down some dependence on the tidal field. So that will introduce some tidal bias. And these bias coefficients are basically nuisance parameters that capture different correlations between the underlying dark matter field and the galaxy field. And the principles we're using here are, well, first principle is the symmetries. So for instance, in this bias expansion, you cannot write down the velocity field just because, well, it's a vector and the density field is a scalar, so it doesn't have the velocity field doesn't have a proper tensor structure. And another example is that you cannot write down the gravitational potential because the gravitational potential is not a different variant quantity. So like physical observables cannot depend on this, right? It can only depend on tidal field. So basically the equivalence principle requires that there should be no dependence on the gravitational potential on the right-hand side. So this is how we take advantage of symmetries. And just we're writing down Taylor series. So we're writing down all possible fields, linear order, second order, cubic order, etc.
So just a super dumb clarification question. When you say you can't write the gravitational potential, you mean on its own? Because I guess the tidal field has the gravitational potential. You just mean it can't be an isolated term, but things can depend on the gravitational potential via its derivative.
Yeah, with two derivatives here, the tidal field is a physical field, whereas the gravitational potential is not. Right, and this expansion on the right-hand side basically will depend on this large-scale degrees of freedom that are introduced, like underlying fundamental fields, such as the dark matter density and, the tidal field. Now, obviously galaxies that we observe, they represent the discrete tracer, and the dark matter field is continuous. So whenever you're trying to sample something continuous with discrete points, there will be some error. And this error is captured by introducing the stochasticity terms. So this epsilon field, you can think of this as an error field. So it's a difference between the dark matter realization and the galaxy density. So it's called stochastic because it doesn't correlate with the initial dark matter density field. So you see that when you sample, dark matter field with galaxies, your error has to do with galaxies and not with the dark matter field. And then, in the spirit of this perturbation theory, we can write down, higher order terms. We can, for instance, couple the stochastic field with the deterministic field at some point, write down epsilon delta. This is like a nonlinear correction. And then we can, continue and write down more complicated dependencies. And basically, the whole idea of AFT is to use the same principles, symmetry, stellar expansion, large-scale degrees of freedom, use them everywhere. So if you want to describe RSD, at some point there will be something that you don't know. You just write down Taylor series based on symmetries and degrees of freedom. And we use this approach everywhere. And basically, one thing that I should mention is that in this EFT, there will be some nuisance parameters, some free coefficients that capture the ignorance about the small scale physics. So these coefficients B1, B2, BG2 is something in the EFT that parameterizes different galaxy formation models. In the context of halo occupation distribution, or let's say hydroseams, in principle, these parameters will be predicted by the theory. But in the EFT, we're totally ignorant about them. We just have to marginalize over them. So that's why EFT, kind of by construction, is very limited. So it's a very conservative approach because it can take into account the symmetries. Basically, it's a very generic argument. But then also it's limited because you don't. It's kind of maybe a bad thing that you don't make any assumptions about the galaxy formation physics.
Is epsilon a known? Is it a free parameter as well, or is it something that if you know the number density of galaxies, epsilon?
What we can measure the some correlation functions of epsilon. So if you calculate the 2-point function of epsilon, this will give you the shot noise. But then because of the exclusion effects, basically, the epsilon squared, the power spectrum of epsilon is never equal to the shot noise. Like there will be some coefficient. So I would say that we have some idea from galaxies what this epsilon is, but ultimately you should also think of this as extra parameters.
You've got epsilon and then epsilon delta. Are they the same epsilon, or should it be epsilon 1, epsilon 2?
Well, in principle, there should be different coefficients in front of them. Yeah, my last slide, it was more designed for a discussion to say some pros and cons if you want to use the EFT. It's agnostic about galaxy formation, and then it gives you very high accuracy in large scales. And it's nice to have analytical control where you can calculate everything, like the covariances and everything. But also, it's very limited. It's it breaks down small scales. It introduces this natural basis to describe higher order endpoint functions, which is endpoint functions, bispectrum, trispectrum, and so on. But then it's pain to deal with this because, well, typically these higher order endpoint functions are large data vectors. For instance, bispectrum has many beans, and in principle, yeah, you can work with it, but then it's really hard. Again, as I mentioned, like by construction, it's missing significant amount of information that is sitting on small scales. So it's kind of by design in this challenge, EFT should be the most conservative and should give the worst error bars on everything.
Great, thank you. I'm Enrique Payas. I'm a postdoc at Waterloo Center for Astrophysics. And as Misha just said a few minutes ago, many of the teams in the challenge relied on simulations to calibrate or to train and validate their models. And the simulations are mainly dark matter simulations, so we need a way to populate those dark matter halos with galaxies. And when it comes to that, there are different methods that you can use to build mock galaxy catalogs. We have something called semi-analytic methods. A few examples of those are Galform or L-Galaxies or Shark. And these methods, they follow a simplified yet very well physically motivated prescription for gas cooling, star formation, supernova feedback, galaxy merging. And so they make use of this these halo merger trees from the simulations to generate samples of mock galaxies. Although these methods are very powerful, they can also be computationally demanding if the goal is to build very large ensembles of simulations with very large volumes to train the emulators, which is one of the things we care about for many of the statistics we look at in this challenge. So there are also semi-empirical models such as subhalo abundance matching or the halo occupation distribution. This is not a complete list. There are other more sophisticated methods available. But the idea is that these methods, they have more simplified prescriptions to populate dark matter halos with galaxies, but at a reduced computational cost. So this allows them to probe many different regions of the parameter space very efficiently, which is especially suitable if you want to build large ensembles of simulations to calibrate or test models. So as I said, many analyses in the Beyond 2BT challenge, including KNN statistics, density split clustering, and the simulation-based inference rely on these semi-empirical models, and in particular, they rely on this halo occupation distribution or HOD for short. So HOD is a statistical model that tells you how many galaxies you should assign to each dark matter halo in your simulation. And in its most basic form, this expected number of central and satellite galaxies in each halo only depends on the halo mass, which is exemplified by this model in the bottom left corner. However, we nowadays know that galaxy formation is more complicated than that, and we know that the number of galaxies that each halo has not only depends on halo mass, but can also potentially depend on other properties as well, such as the halo formation time, or even what's the local environment in which the halo lives in, right? So the current HOD models also allow for this extra flexibility by adding more degrees of freedom to incorporate other effects that, such as assembly bias, which kind of tackles this effect of halo formation time, for instance. Apart from knowing how many galaxies you should put in each halo, you also need to follow some prescription to know how to assign the positions and velocities to each of those mock galaxies. And there are different ways of doing this. In particular, for this challenge, the positions and the velocities of the central galaxies are always matched to the position and velocity of the center of the dark matter halo in which they reside. But when it comes to the treatment of satellites, different teams follow different approaches. So the simulation-based inference team assigns their satellite positions to be within the virial radius of the halo, following a Navarro-Frank-White profile. And they assign the velocities to the satellites by solving the James equation. In the case of the density split and the KNN teams, the positions and velocities from the satellites come from randomly sampled dark matter particles that are bound to the halo. Having that said, all of the HOD models that we used for this challenge have the flexibility to also relax some of the assumptions about this assignment of velocities by including parameters that regulate whether there could be an offset between the velocity of the halo and the velocity of the galaxy. So they also incorporate degrees of freedom that allow you to relax some of these assumptions.
The HODs can be kind of calibrated against these large hydro simulations as well, right? To show that they aren't just completely made up by us, that they do actually manage to match the way galaxies populate themselves amongst halos, that it is actually a reasonably good description.
Yes, indeed. I think that's a very important validation that other studies have tackled. In the end, we want to ensure that HODs or the sham or any of these semi-analytic methods have enough flexibility to fit the clustering from more realistic galaxy formation models. So validating against the hydrodynamical simulations is a very important step. There are many studies in the literature that have explored this kind of behavior, whether the HODs are able to mimic some of the properties from the hydrosims or not. In this challenge, we have not included any of those hydrodynamical simulations to test again, but that could be something interesting.
I guess the consensus in the community at the moment is that hydrosims are good enough to test that your model is like robust in the sense that it can fit them, but they're not good enough that you can measure the parameters from them and then go to the real world.
I think that's fair, yes. And in addition to hydrosims, there are other frameworks for galaxy halo connection modeling that you can do this sort of internal self-consistency tests with. And I would also add that the physical motivation for the HOD depends on the selection. So for different selections, they're more or less sort of secure.
So for the actual analysis of the challenge data with EFTP plus B, our standard data vector for redshift space MOX consisted of five statistic. Well, we use three multiples of the galaxy power spectrum, monopole, quadrupole, and hexadecapole. Plus, we use this Q0 as a new statistic. It's a real space proxy. So basically, at some point, if you just work in redshift space and use multiples, at some point you get sensitive to fingers of God that limit the application of perturbative technique, but then you can construct a proxy for the real space power spectrum and extract a little bit information at higher case that like typically is spoiled by fingers of God. So you can cancel fingers of God with this Q0. So you can think of this as an extension of the power spectrum. And then we add the bispectrum monopole B0. For the covariance, we use the Gauss analytic covariance, which is fine on large scales. For the data estimator, we use the window-free approach developed by Oliver Hilcox for light cones and the usual Scacchiumara estimator for periodic boxes. So for us, it's also a test of the estimator of the different statistics. So this is another dimension in this challenge. And for the model, we use one loop EFT for the power spectrum and Q0 and the tree-level bispectrum. We also tried one loop bispectrum, but then it was not very useful because it depends on around 40 nuisance parameters. So at some point, just all the information is dumped into them.
The Baku emulator hybrid model team is composed by Matteo Zenaro, Raul Angulo, and myself. In a nutshell, we make use of the power spectrum in real space and power spectrum multipoles in redshift space measured from the galaxy distribution of the MOX. In contrast to other traditional techniques, we don't discard the data from small scales. Specifically, we account the data down to scales of about k of 0.5 h of a megaparsec, which are in the nonlinear, non-Gaussian regime. From earlier studies, the strongest dependencies of the power spectrum on omega matter and the Hubble parameter are on the large scales, so we don't expect to get much more information on them by including these smaller scales. However, sigma 8 does have a dependency on smaller scales, so we would expect to get tighter constraints on this parameter. And that's what we see in this work. We achieved the incorporation of the nonlinear information by proposing a model that is a mixture between n-body simulations and analytical approaches. On one side, the formation of structures on a cosmological level is done with an n-body simulation. This gives an exact prediction on the distribution of the dark matter density. On the other side, the galaxies are placed on top of the dark matter density following the analytic relations allowed by the basic symmetries in the equations of galaxy formation. This is a model that allows for field-level analysis. However, it requires an n-body simulation per set of cosmological parameters explored. This makes it very slow for traditional analysis, and we have to resort to neural network emulators. Right now, we only have emulators at the power spectrum level. This is the reason why we stick to these statistics in the collaboration.
The EFT API team analyzes the real space mocks directly at the level of the galaxy three-dimensional field. Our data vector consists of all Fourier wave vectors that represent the 3D galaxy fields. Our parameter space consists of the entire set of Fourier modes, plus the sets of cosmology and galaxy bias parameters. The motivation behind field-level inference is to access only information in the data. There's no data compression, so there should be no information loss up to the scale cut of the model and the likelihood. In a recent paper, which you can find more details about by clicking on the thumbnail, we show the field-level statistics provide a very significant improvement over the standard power spectrum plus bispectrum statistics when quantified in terms of constraints on the parameter sigma 8. The model and inference framework we use is the Lagrangian EFT-based forward model of cosmological fields, aka LabField, developed by the LabField group. Here, the group is represented by the EFT API team with two members, Fabian Schmidt and myself. The LabField forward model starts from Gaussian initial conditions and follows the gravitational evolution forwards with Lagrangian perturbation theory. Model prediction for the galaxy field can be constructed either in Lagrangian or Euclidean space through the EFT-biased expansion, connecting the matter and galaxy fields on linear and quasi-linear scales. The small-scale physics are either suppressed or marginalized over, in which case they contribute to the stochastic field epsilon. This stochastic contribution is captured by the EFT likelihood. LabField is very fast and efficient. Even better, it is differentiable. This allows us to perform Bayesian inference using gradient space sampling methods like the Hamiltonian Monte Carlo HMC. For our validation tests within this data challenge, please see the longer video.
Hello, I am Enrique. I am a postdoc at the Waterloo Center for Astrophysics, and together with Carolina Cuesta-Lázaro, who is a postdoc at MIT and Harvard, we carried out the density split clustering analysis for this challenge. The idea of density split is to characterize how galaxies cluster on different environments of the cosmic web. So we start off by generating random query points in the cosmological volume, and we measure the local density of galaxies around each of those points. We then proceed to split the query points into different quintals according to their local density. So for instance, from this figure, we can see how the first quintal, shown on the left, is probing low density environments in the large scale structure akin to cosmic voids, whereas the last quintal on the right is probing high density regions akin to clusters of galaxies. Once the query points have been split by density, we can then calculate clustering statistics for each of them separately. In particular, there are two statistics we focus on. The first one is the autocorrelation function of the query positions in each quintal, as exemplified on the left. And the second one on the right is the cross-correlation function between the query positions and the redshift space galaxy field. Here is how these different statistics look like in practice. Here each color is representing a different density quintal, and as you can see, we have access to most of the standard features that you would find in the standard 2-point correlation function, such as the baryon acoustic oscillation bump around 100 megaparsecs over age. But the idea is that by probing each environment separately, we gain sensitivity to non-Gaussian features of the galaxy density field, especially on small scales. And in previous work, we have shown that this can lead to substantial improvements in cosmological constraints compared to the standard 2-point clustering analysis.
Hello everybody, my name is Carol Cuesta-Lázaro, and I'll be introducing work done by Sandy Yuan on K-nearest neighbor statistics. Sandy was looking at what is the probability of finding a kth neighbor around a galaxy at any given pair separation. So in particular, you can see here on the right-hand side a two-dimensional distribution because he was splitting separations along the line of sight and perpendicular to the line of sight to be sensitive to the effect of redshift space distortions. But here what you see is the cumulative distribution function of finding a galaxy, a second neighbor, at any given pair separation. So go from 0 to 1 on large scales where you found all your second nearest neighbors. This is how it looks like when you place yourself around a galaxy. This is what here refers to as the DD k-nearest neighbor, or data, meaning the galaxies. But you can also place yourself around a random point in the survey volume. So this is called the RD k-nearest neighbor, random data. In this case, you'll be sampling the volume of the survey, which is mostly consists of voids, so you'll be more sensitive to what's happening in underdense regions, whereas the DD flavor will be more sensitive to the halo galaxy connection, or what the galaxies are doing on small scales. The shapes of these 2D distributions, like the one you see on the right-hand side, can be used to constrain cosmology, and in particular, somebody found that is very constraining of sigma 8. Finally, I'd like to draw your attention to the very cool paper that Sandy wrote about how we could validate our smaller scale modeling of the halo galaxy connection by fitting some statistics and predicting others. If you really found a robust way to model the halo galaxy connection, you should be able to make predictions with it. In particular, he was fitting the DD flavor of the k-nearest statistics and predicting the RD flavor. Here you can see 3 different models of the halo galaxy connection and how one of them was doing much better than the other. But if you'd like to learn more about this, I suggest you look into the paper at the archive. Thank you.
Hi, I'm Chirag Modi, and I'll discuss the simulation-based inference component of this mock data challenge. And this was work done by me and Chang-Woo Ha. So simulation-based inference has become increasingly popular in cosmology because it does not rely on making any assumptions on what the distribution of your data looks like. So for example, it doesn't rely whether your data is Gaussian with some known covariance or not. Instead, it tries to learn the likelihood distribution of the data directly from high-fidelity simulations using neural density estimators. An advantage of this is that we can now use any statistic in any regime that can be simulated, and we are no longer restricted to having a theoretical model for these statistics. So for this mock challenge, we used power spectrum multipoles and bispectrum, and we used them up to the small scales of k of 0.5, where we do not have theoretical models from effective field theory or perturbation theory so far. A flip side of this, however, is that because we are using simulations, our final analysis is limited by the quality of the simulations that we use. So for this mock challenge, we used Kyoto simulations, which is the largest simulation suite we have available in cosmology for SBI. But every individual simulation in this is basically 1 gigaparsec in volume. This is much smaller than the 8 gigaparsec volume which was used for generating the mock data for this challenge. And as a result, the simulated data that we used for training a simulation-based inference procedure had much smaller signal-to-noise ratio than the mock data for analysis, especially on the large scales. And this is reflected in our results, which are shown here on the left, and our contours are much broader as compared to the other exercises because of this lower signal to noise in the training simulations that we used, especially for omega matter, which is much more sensitive on the large scales than sigma 8.
Hi everyone, I'm Giovanni Verza, and I will present you voice statistics used in this challenge. This work was made in collaboration with Sofia Contarini, Nico Hamaus, and Alice Pisani. Cosmic voids are the large underdense region in the galaxy distribution, and this team focuses on constrained cosmological parameters using void statistics. The reason of that relies in the complementarity of cosmic voids with respect to standard statistics such as the 2-point statistic of galaxies, and it has been shown in the literature that cosmic voids provide extra information. In particular, they show some orthogonality in the parameter space. For this analysis, we detect voids in the galaxy light cone, and we consider 2 different void statistics, the void size function and the void galaxy cross correlation function. The void size function is the number density of voids as a function of the size, and the statistics mainly depends on the matter power spectrum. It is possible to theoretically predict the size distribution of voids reaching a fixed value in their density contrast of matter, And to match this theoretical definition, we post-process our void catalog in order to have the void radius reaching a fixed density contrast in the galaxy distribution. The other statistics is the void galaxy cross-correlation function that can be measured by stacking the void density profile in the galaxy distribution. From the cosmological principle, we can imply that stacked voids are spherically symmetric, and so they are statistically isotropic in real space. So they can be used as standard sphere to measure the distance ratio through geometrical distortion sourced by the Alcol-Paczynski test. And in this way, we can use the void galaxy cross-correlation function to constrain the expansion history of the universe. Above that, we are also to consider anisotropy sourced by redshift space distortion, but for more details on our theoretical model and on our validation test, please check out the longer video. Thank you.
From the question that you asked before, Sean, about like if we were a bit nervous at the day of unmasking, the answer is yes, I was terrified. And the only reason why I was not hiding behind a blanket was because I knew that we agreed that there was a second chance if someone had made like an obvious mistake or something that it was clearly easy to do, right? And to be honest, I think that arguably, like this is like the most important part of the project, right? Because it is where you learn about your model strengths and weaknesses, and this will lead to extra projects and to see if one can solve possible biases that you have found, or get extra information from more aggressive choices, right? And let me give you an example of how to identify problems and how to look for solutions, right? So these plots that we are showing here are exactly the same plots that we had before, but with some shaded constraints included, okay? So these shaded constraints represent post-unmasking results. So the results that we got after we knew if we were biased or the precision of our procedures with respect to other procedures. And as you can see, the BACO P, which is the one in which I was involved, found that if we removed the hexadecapole, our contours moved by about half a sigma, okay? And it doesn't sound like very important, but if one takes into account that we are overinflating our errors because we're using the mean of 10 boxes, while using only the error of one of the boxes to reduce as much as we can the cosmic variance, these shifts are actually important. Okay, so we are talking about shifts of 1 to sigma, some more or less like that. So exactly, so we found out that the hexadecapole was giving us some problems. The problem was that we were not accounting for the emulation error properly in the hexadecapole. So when we removed it, we were moving exactly in the correct direction. And just by using the monopole and the quadrupole, we were able to reproduce the results quite accurately.
It's a flaw here, I suppose, of the emulator method, that if one of the other methods had noticed that there was some issue in the hexadecapole, they could try and tweak the model. But I guess with an emulator, you don't have that freedom. You'd have to recreate the entire emulator. So all you can do is remove the data. Is that maybe a fair observation?
No, it is a fair observation. It takes a while to reconstruct the emulator. But the problem of this one was actually the misspecification of the error that we expected from the hexadecapole. Yeah, so if we were able to account for that error in a more robust way, in principle, we could include it back.
Yeah, the two tests that we did were as follows. So first of all, when we ran the CFT analysis, we're doing a Bayesian analysis. We have to introduce some priors and cosmological parameters, and all teams basically used very different priors. And I think that in the CFT analysis, we use the widest priors just because we can calculate for any cosmology. And actually, it's kind of a bad choice in this particular instance because we're there are some degeneracies that are not broken, and we're exploring a lot of cosmologies that are beyond the, very far away from the true one. So if we, for instance, if we restrict our priors to match those used by BACO, then we can remove some of this dependence on priors, and then you can see that the CFT kind of results shift even closer to the true. So again, as Marcus mentioned, here we cancel cosmic variance, so kind of the deviation of the mean best fit from the ground truth comes from systematic error. Like most of it comes from systematic error. So you see that we can reduce some residual systematics by homogenizing the priors. And the second test that we did had to do with the results for the real space. So in real space, we had these two different EFT flavors. We had the field level technique that Min introduced and the classical P plus B, and they were sort of different. The most striking difference was in terms of the error bars. So the error bars of the EFT P plus B were substantially worse, despite the fact that nominally we're using more modes and we're going to higher Kmax, both for the power spectrum and the bispectrum. We're trying to understand what causes the difference. And at least one of the sources that is important is precisely stochasticity, treatment of stochastic terms. So in the EFT, we take into account the fact that, the stochastic epsilon field has a bispectrum, and also there is a coupling between epsilon delta coupling. So there are additional parameters you need to marginalize over. And this is something that was not done in the context of the FBI method that Min maybe will explain in detail. So once we do the same thing, if we just ignore these terms, the higher order statistics generated by the epsilon and also contributions from the epsilon delta terms in the bias expansion, then at least we can reduce the error bars. In the context of the FTP plus B, this also biases our results. So I should say that this P plus B restricted analysis, where we basically turn off all these extra stochastic terms, is like centered at the exact same mean value because the actual results are biased. So we see that for FTP plus B, these stochastic corrections are important. You cannot ignore them. But in terms of the error bars, we got a good match. So I think that at least it gave us the intuition that probably these modeling choices, they are important. And once you kind of homogenize them between the two approaches, you get at least the error bars very similar.
Can I just dwell one more time on this mean of 10 realization thing and the different definitions of 1 sigma? What is being plotted here then is the error that you would get if you the statistical error, you would get if you only had one realization to measure off. It's not the actual statistical error of these data points that you're plotting. You're just showing for visualization purposes what the statistical error would be if you only had one realization. And so therefore, when we're interpreting this, as you said yourself, Misha, almost all of the deviation from zero in this will actually be systematic errors in the method. But if it's still within this visualized 1 sigma, that's kind of not a problem because in the real world, the statistical errors would be that large, so comparable to the systematic errors. Is all of that like true?
Yeah, I think that's fine. I mean, I think that's the statement that we are making is basically the constraints that we're reporting is the uncertainties that we would associate to our constraints in a real world scenario where we only have one realization. But any shift from the ground truth, you should multiply by like 3.16, right? You should think of like 1 sigma here away from the ground truth as like 3 sigmas. Yeah, so just to finish what Misha was referring to, so going from the pre-unmasking to the post-unmasking analysis, we are going from the constraints, the EFT API to API extended constraints. And what we changed is basically 2 things. We went from second order to third order bias expansion, so having more terms in the bias expansion that Misha explained. And then the second change is basically opening up the stochasticity and now jointly infer and marginalize over the stochasticity. In the official pre-unmasking analysis, we assume that the stochasticity follow the Poisson distribution. So exactly like what you said before, given a number density of the tracers, you can work out exactly what is the expectation for the stochasticity, and that was the assumption. In the post-unmasking analysis, we now allow for that additional degree of freedom and marginalize over it.
Looking at these plots, perhaps KNN is also a little bit off in the omega matter, and there was no post-unmasking thoughts by those groups?
I guess there was no post-unmasking, but I think there were some very interesting validations on how the KNN is very constraining, which means it's also very sensitive to what's happening on a small scales. And I think as opposed to density split, we were also using a very similar simulation-based setup, but we were also including the large scales. So although it says S min equal 1, S max is 150, whereas KNN was solely using small scales. So it is more sensitive to what's happening with the halo galaxy connection.
If you were to start again with your method, and also if you were to start again with the actual whole experiment of having the masked mocks, what would you change?
I think something we've thought about a bit during the challenge is what should be the question that the next challenge is set out to answer. And for that, what we're thinking is what we really want to know is what is the robust information we can actually get from galaxy surveys, right? And we've discussed a lot about this, right? The halo galaxy connection is still the most important known unknown in the sense that, especially for these beyond 2PT statistics, most of them, as you've seen, are going to nonlinear scales. Also for BACO, right? The improved constraints we're getting come from analyzing those nonlinear scales. So we really want to understand how robust is that information. And for that, we need to go beyond this HOD assumption, right? So here we were analyzing one mock with a particular HOD that we were not given in advance, but still we knew it was an HOD model. So we really need to create a suite of galaxy formation simulations with large volumes, which might be challenging, but we really need to go in that direction to learn about where the robust information is. And I think what's interesting as well is to then think about how these beyond CPT statistics that might not be super robust on a small scales can tell us something interesting about galaxy formation. Right? The fact that they're more robust means they're very sensitive to it. So maybe we can utilize them in interesting ways.
Mm-hmm, mm-hmm. Like stop being cosmologists for a while and become astrophysicists and say, maybe we can't constrain omega matter, but we can, well, or at the same time, we can constrain actual galaxy formation stuff.
Exactly. The thing is that we can constrain it, right? We see the information is there, but it's not robust because we're not modeling galaxy formation correctly. But if we build a set of diverse galaxy formation scenarios, maybe we learn how to do these things well to get there.
The way I see this, there's like two kinds of challenges that one can pose with this information. So one of them would be kind of like a general challenge, right? Like a challenge in which you test your model or your models for a wide variety of galaxy formation physics, as Carol was saying, right? Like you can use hydrodynamical simulations, one can use HODs, one can use semi-analytical models or whatever thing that you can think of, right? And this will test the generality of your model and how well can it fit any kind of galaxy formation physics. But there's another way, which is like having very specific challenges for a given set of data. So let's assume that DESI has a very weird and unique selection function, and then what you end up with a very good mock that is able to reproduce like every single detail of that simulation. If that's the case, you just need like have everything under control, right? Like the systematics and everything, and then you can try different models on that. Models that might not work for the generality, but might work for the specific survey. However, one has to be very careful with those things because maybe you're not getting all of the details of the survey correctly. So that's why these general challenges, like the one that we performed here, are super relevant because that's the kind of things that they test. What if you didn't get in the mock, resembling DESI, the right galaxy formation physics?
Things that I would like to see for the next challenge. First of all, the simulations exist to have more realizations in ΛCDM, so that's definitely desirable. It's just work, basically. And then also it would be interesting to explore extensions, deviations from ΛCDM. So in some cases that the simulations exist already for WCDM. There are other things that are interesting in that context. And then I think for me, the thing that I've spent the most time thinking about is the sort of spanning the plausible space of galaxy formation models. So we have a particular HOD form in the three different sets of mocks. The parameters may take different values, but we have one form in this challenge. So there's tons of plausible HOD extensions that we can explore. And then also, like Carol said, there's other galaxy halo connection frameworks that if we were to actually use multiple at the same time, then we would eliminate the possibility of, for example, someone getting lucky, luckily, serendipitously choosing the same galaxy formation model that produced the mocks. And then, the outcome of that set of mock analyses could break in any number of ways, but definitely comparing, like how the HOD-based methods work on, say, the hydrosim or the abundance matched or semi-analytic model mocks, there's interesting conclusions that can be drawn. I don't think of it as like stopping being a cosmologist temporarily to be a galaxy formation person. I think that this is really about merging the two fields, because there's a lot of information in galaxy formation physics that we could use to constrain, either the HOD or even the nuisance parameters in the EFT frameworks. And then another thing I want to add along this line is that with more sophisticated models of the galaxy halo connection, we would then potentially be able to actually model galaxy properties that are used in surveys for selection. There are multiple advantages of this. So one is that, for example, I'm interested in clusters, and so most cluster finders rely on the red sequence in some way. So if one were to look at novel statistics that involve clusters, you would need that information in the mock catalogs. And then also, the more that we can just allow the analysis teams to define the selection and do the validation and then incorporate whatever information they're comfortable incorporating from galaxy formation is good. So that, I think, would be very nice, is to have more complex models that can actually model photometry and other selection, properties that selection is done on. And also lensing would be nice. The most straightforward way to incorporate that would be actually able to produce ray traced shape catalogs that we could provide to the participants. And there's code to do that, but I'm not sure how easy it is to run, but it's a possibility.
I just want to quickly add that all these will actually take a big group of people, right, in a community. That this is important because we're talking about running all these simulations to assess our confidence on the error bars, running different galaxy formation models, potentially hydrosims, large volumes. So it really will take a big group of people to carry this out. And I think that's why it's important to get a community like this one together to do this.
Yeah, so on another point, more so than making all these different statistics compete, I think there is a lot of hope in combining them in the future. The question of how to optimally combine these different statistics, which are extracting information from the same underlying data, is, I think, highly non-trivial. So from many of these contour plots that have been shown, these different statistics follow different degeneracies in the parameter space, so there is a lot of hope in combining them. But it's not entirely clear what's the correct way of combining different methods which follow different parameterizations. I think Misha and Carol have a very nice paper of how to potentially combine EFT with HOD approaches. I think Oliver and Chirag have a similar paper on this regard. And it turns out that it's not something easy. Even the question of how to optimally combine the large scale information with the small scale information, with these two different approaches, in which on the one hand you have this EFT model that have all these bias, expansion terms and so on. On the other hand, on small scales, you have the HOD parameters. And even though they are trying to extract information from the same galaxies, like the parameterizations are different, and it's not entirely obvious how to combine them in order not to repeat the information. So I think there also needs to be like an effort in terms of assessing how to optimally combine these different statistics in order to get the best possible cosmological constraints in the future.
I agree with both Carol and Marcos that for the next challenge, ideally we want to span like a bigger parameter space, not only cosmology, but also like galaxy matter, galaxy halo connection. But we also want, on the other hand, we also want that parameter space to be consistent with different observations, right? Or to put it another way, we want those parameter space to reproduce like the clustering statistics of galaxies that we actually see in the spectroscopic surveys. And also maybe, for lensing would be, pre-produce what we are seeing in lensing surveys and KSZ, CMB surveys.
Like all the other analyses, our problem was to model the smaller scale, the smaller possible scale. And these small scale are affected on how you populate your halo galaxy connection. And so one of the points that arises from our analysis is that we have to acquire confidence on modeling a smaller scales, and in particular this galaxy halo connection. And one point that arises in the discussion among our group is that now, for example, LASI, Euclid, and the future ROMAR, so this new generation galaxy clustering analysis, are exploring the emission-like galaxies, where the uncertainties on the halo-galaxy connection is even higher. So one point we want to address, we would like that this challenge allowed us to address is how to marginalize over this galaxy halo connection and how to go to smaller scales. Yeah, the other point is how to combine the various statistics, and we try to do something, or better, in the literature we have explored something concerning voids and standard 2-point statistics, and for example for Euclid, but even for other surveys. And what is interesting is that, for example, voids and 2-point statistics are really orthogonal to each other in some parameter space. For example, if you look at the sigma 8 omega matter plane, voids and galaxy clustering statistics are really orthogonal to each other. So there is a lot to gain combining various statistics.
I guess in some ways that's not surprising, given that one is measuring the locations of things and one's measuring the lack of location of things.
Yeah, this is one point. Yeah, but it's not only that. One over density, the other has under density, but it is not the only reason. Galaxies are, let's say, point-like in your analysis. Voids are extended, so are sensitive to different geometrical different effects, and also different systematics. So
okay, I just wanted to expand a little bit on what Carol and Giovanni just commented a bit about. So when people are going to see this paper, they're going to see figure 1, and they're going to see like a bunch of 2D contours, and they're going to see like different sizes, different degeneracies, and so on. And they're going to ask, where's the information coming from, right? And Carol and Giovanni have both said something very interesting, which is if you push to smaller scales, it seems as if you are becoming very sensitive to those scales, but also gaining a lot of information. Now, the question that one can ask is, do you gain more information by going to smaller scales or by including extra statistics? And this paper do not have a definitive answer on that, but points towards some direction. At least from the BACO perspective, it seems that if you keep including smaller and smaller scales, even if you only use 2-point statistics, you don't gain anything on omega matter, okay? But on the other side, sigma 8 is actually sensitive to these smaller scales. So you keep gaining information if you can include those cases, right? But from the different comparisons, it seems as if it's important to include extra statistics, and it's always good to include extra statistics, but the smaller scales seem to have like loads of things to say still.
So, yeah, as Michael says, I think we really don't know. This challenge wasn't intended for a comparison on information content, which means the priors were not comparable, the ways we estimate covariances are not comparable. There's so many things that are not comparable. And actually, if you look at papers of people that have compared 2-point statistics with this beyond 2-point, when those assumptions are kept the same, people always find additional information, right? I think we have many, many examples of that. So I think we have to be very careful with what we read from here, right?
It would be really nice to test the discovery capabilities of these different methods. It would be nice to run a challenge with some new physics injected in it, like early dark energy or some ultralight axion dark matter or primordial non-gaussianity, and then use whichever method you want. Like, can you detect this new physics? Okay, I think that for me, only this kind of test will really tell you like what method gives you more information.
You could also do it with like multiple different ones. You could have 10 different ones.
Yeah, because one example is primordial non-gaussianity that you will not you can get the power spectrum very nicely. You can produce an emulator measured to extremely small scales. You'll not be able to see it, or like it will be very hard to extract non-Gaussian signal from power spectrum. But then the bispectrum shows up already on very low K, so large scale. So this one example that shows you that the question about information like depends on what you're looking for.
Do you not get the scale dependent bias in the power spectrum that would be?
No, you get, but it's very tiny. For the equilateral type of non-Gaussianity, for instance, right? Then you will not see anything. Yeah, this is what I meant. And or the parity violation, right? There was a whole workshop that you organized at some point. Like, this is another example that you'll never be able to see anything, in the power spectrum. Also in the bispectrum, you won't be able to see anything.
To add to what Misha was saying, I agree that kind of challenge would be extremely interesting, but it would also be very challenging because not every analysis team is set up to, for a particular sort of strange new physics deviation from ΛCDM. It's not a given that every analysis team is actually prepared to do inference and actually constrain that scenario. And also producing the simulations that's a smaller challenge since it's sort of a single point, but it is extremely interesting. I think that's definitely something that we should try to move towards in the future.
Density split statistics seems like the kind of almost when we're talking about combining methods, it seems like the ideal thing, because in some sense it's density split, and then the word statistics can mean whatever you want. It could be density split effective field theory, density split field-based inference, density split voids. So you can just do any of the other methods and then ask what you get in these density bins.
That's an excellent question as well. In fact, the way I approached this density split technique in the first place was because for my PhD, I started working on void statistics. So at the beginning, I was only looking at the underdense part of this whole picture. But then I was really curious to see whether I could find some other interesting things by looking at the other environments. And then we thought, okay, maybe we can generalize this to all environments and combine this thing. But it is absolutely correct that one could envision like adding even other statistics to build kind of an ensemble of different statistics that could break parameter degeneracies in different ways. I think one of the motivations of combining these different environments is that there have been different papers showing that, for instance, the low density environments could potentially be more sensitive to neutrinos because the fractional contributions from neutrinos seems to be larger on voids than compared to other environments, because the volumes that the voids are probing are so vast that just the neutrino free streaming scale, it is much more likely to have neutrinos affecting those environments more. And by combining these low density regions with other high density environments, which could perhaps be more sensitive to galaxy formation physics, I think you get the best of both worlds. So I think this idea of combining different things is something I like. But while from the information content point of view, it's something positive, it also becomes challenging from the fact that different environments could also be sensitive to different systematic effects like observational systematics. And that's something that you have to worry about as well. Maybe the high density environments are more sensitive to like small scale fiber collision effects from spectroscopic surveys, and how you consistently model all these systematics when you combine all these things together. I think that's a point that needs to be addressed carefully. So yeah, I think one has to find a balance, I guess. As you keep adding more and more things to your data vector, then things get a little bit out of hand, because the covariance matrix then is also very large. So there are many different things that need to be like balanced when it comes to finding the optimal combination of statistics.
Yeah, my last question is, I guess, to do with systematics. How much of they've sort of been alluded to regularly, but they weren't there in the mock data, which sort of surprises me. How much are they the elephant in the room? Like, are you implicitly just assuming that, okay, that's the observational surveys problem? They have to make sure that they remove the systematics as much as possible, and then we'll come along with our methods and we'll analyze their data. But presumably there are degeneracies between systematics and the data, and systematics and the method, and systematics and the data and statistics in the method. Should this have been done where it really is saying, no, this is a DESI survey or this is a Euclid survey and here are the systematics? Is that impossible because you don't yet know what their systematics will be? What is the robustness of your results when you haven't included systematics?
I mean, in DESI, right, one systematic is the weights that you have to apply to correct for the fiber assignment. So I think those are treated as sort of like a modular, right? Like you said, right? Like we're sort of implicitly assuming that those weights can be properly estimated, and that itself is a huge challenge and a lot of work and requires a lot of expertise. So there's also a practical element of not including systematics, I think.
One systematics that it would be interesting to be explored for voids is the simple mask. Voids are extended objects, and they're really sensitive to the masking of your survey. Because if, for example, a void that can be from tens to hundreds of megaparsec of size, if touches your mask, you have to throw it out because you don't know its actual extension. So in future challenge, we would like to estimate the impact of the mask on our void sample, and now can we account for that, how it impacts our final results and so on.
Yeah, I think you raised a very good point, and I just wanted to say that many of the ways that we have when it comes to mitigating known systematic effects, such as fiber assignment, have only been extensively validated for 2-point statistics. So it is definitely a challenge to address how to optimally mitigate those effects for all these other new statistics. And it would be really cool to be able to test that in a future challenge.
Yeah, I completely agree with Enrique. I think we can't assume that the surveys will clean up the data for us and then we'll just analyze it, right? Because it's a non-trivial thing to do. I think there are two approaches here. So in cosmology, so far, we've been cleaning up the data, right, with these weights, different ways to do that. But I think the alternative is to build very accurate forward models. So have a forward model for DESI, in particular for the kind of approach that we're following, using simulations to model the data, we could actually very easily add a forward model to that, right? And our modeling wouldn't change at all. Now, the question is, yeah, we could very easily add a forward model, but who will build the forward model for, let's say, DESI? I think there are different bits and pieces, and the collaboration is working on putting these things together, but it's obviously a very challenging task. And in the future, I think it'd be very interesting if, in the same way that we commission a telescope, we also commission a forward model of what the telescope is doing, so that we have very, very usable software that is actually fast and efficient that we can use as a forward model to get cosmological constraints.
Well, I think actually, I mean, that is challenging, but I think it's even more challenging to correct for it. Like I think it would probably be simpler for us to mock up, let's say, the DESI fiber assignment in our light cone, right? I mean, we can literally make little, robots in software and do it, right? But then all of you would have to replicate the very complicated division of labor in DESI to actually estimate the weights. And I think practically it seems very difficult, especially since, like you said, the work required is going to depend on the statistic that you want to analyze.
If you have a forward model, do you not in principle have a backward model? And is that not the solution, that you apply the backward model to the data to get the thing that all of the models we've talked about today are actually modeling?
If your modeling framework is forward modeling the selection, for example, then it's simple to implement, right? I mean, in the sense that if you're training an emulator from light cones that you can put this model on, then it's straightforward. I mean, there may be more creative ways to do it, but I don't think it's a trivial matter of sort of inverting the forward model of the systematics that can be applied to any method, right? I feel like for the analytic methods, it's maybe particularly difficult.
Yeah, the forward model is not invertible, right? So if you think about fiber collisions, you're sampling some of the galaxies in over-dense regions, but to invert that, you would have to revert the sampling, right? So you would have to learn like a posterior over clean data given the systematic observation. So it wouldn't be straightforward. You could learn a posterior, right, and then analyze that posterior.
And actually, I believe in DESI, I think they do have this forward model of the fiber assignment, but it's still a difficult matter to sort of invert it.
Thanks everyone for watching. If you like this, please do subscribe and click the bell to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, there is a supplementary video to this with more detail behind each of the methods. You should check that out. And thanks everyone for the great talk.